Hey guys, I'm going to record this video here going over your lesson just in case you missed it in class or need a refresher. This is going to be Unit 4, Lesson 3. This year in your student packets, that'll be pages 12 through 15. So let's get started. We are going to be talking about observational studies versus experiments and some of the experimental design techniques as well as completely randomized design. So without further ado, let's look at this question here. Last year, EKHS, that's East Kent High School, actually, from Michigan. That's where I'm from. I'm not from there, but I know where that is. They offered an after-school SAT prep class that students could volunteer to take. 44 students took the course and then took the SAT. The average SAT score for this group was 1220. Not bad, not bad. The average SAT score for all students who did not take the prep class was 1050. In the situation described, is this an observational study or an experiment? And explain your answer. So think about that for a minute. What's the difference between an experiment versus an observational study? An experiment is something where you try to show some cause and effect. You impose some sort of treatment, or you force somebody, not force, but you make somebody do something based on some group they're in versus somebody who's not doing something, and then you compare them. In this case, was this an experiment? It's not an experiment. It's an observational study. Students weren't randomly assigned to groups. Treatments weren't imposed. You know, we just got the data from them, and we measured that SAT score from those who did take the class, who didn't, without any other factors, without saying, all right, you go here, you go here, you go here. And there's no random assignment. It's just, hey, those who took it, let's look at their scores. Those did not, let's look at their scores or other factors. So what are the explanatory and response variables? Well, you know, explanatory is X, response is Y. So we're trying to predict if the SAT course showed some sort of improvement on the test scores. So the explanatory in this case is whether or not they took the course. And the response variable would be the SAT score. So SAT score is what we're measuring, right? And the explanatory variable will help predict that. Can you conclude that taking the prep course will cause a student's SAT score to increase? Why or why not? So in this case here, you cannot. There might be highly motivated to learn anyway. Those who voluntarily signed up to take the SAT course probably were going to do okay on the SAT anyway. They have the means and resources. So in this case here, what we need to do is an experiment to show some sort of cause and effect. Okay, we cannot show that unless we actually have something where we can compare two groups without them choosing what they did, and that's something called random assignment. So what other possible variables can you conclude that could explain why the SAT scores are higher for those who took the prep course than those who did not? Think about that. You know, what might account for SAT scores being higher for those who took the prep course other than just the prep course alone? Some possible answers would be all students, of course, might be trying to go into college, so there's a motivation there. They might not have an after-school job or extracurricular activities to slow them down, so they have more time to study and prepare for it. They have rides home from school. They want to do well in the SAT anyway. So there's a lot of things that could factor into that. These are called confounding variables. Confounding variables are simply variables that that contribute to a response, and they could change the response that is not something we're trying to measure. And last, design an experiment that could allow us to determine if the SAT prep course causes an increase in SAT scores. Be as thorough as possible. So what we want to do here is we want to randomly assign people to one or two of the courses. So when you have your group of students, in this case here, let's say we have 100 students, okay? We are going to randomly choose 100 juniors, typo there, to be a part of the experiment. Randomly split them up so half of them take the class and the others do not. Okay, random assignment is important. We don't want them to be able to pick it. We want them to be randomly assigned so they have no control over which one they're going to be doing. After the course is over, all 100 juniors take the SAT. Then you have a basis for comparison. You compare the average scores of the groups. So the experimental units are going to be the juniors, right? And then the treatments, that's going to be the class. All right, whether or not they took the class. Let's explore it on here. This is called a kind of a template for laying out an experiment. This is a completely randomized design. You start with the people, just the group that's going to be doing the experiment, whether they're volunteers or randomly selected. And then from there, you split them up. You do a random assignment, random number generator, names in a hat, whatever. And you split them up into the amount of groups that you're doing. In this case here, we have two groups, one being SAT prep class and two being no SAT prep class. So the two groups are going to be 50 students apiece. You want them to be equal. SAT prep class versus known. And then once we get the scores, we can compare them and we can see, does the SAT prep class show some sort of improvement in the SAT scores? This is a completely randomized design, and we call this the SRS, the simple random sample of experiments. It's not really called that, but that's what you can kind of compare it to. All right, so just kind of filling in the notes and the important ideas. This is on page 13. The explanatory variable helps explain or predict the response. The response variable is the outcome that we're measuring. So kind of similar X and Y's, just we're trying to make some sort of prediction in an experiment. A confounding variable influences both the explanatory and response variables. So they can have a lot of impact on them. We try to minimize confounding variables. So it's really important to have random assignment in an experiment, as well as control, which we'll get to in the next part of the lesson. An observational study has no treatment imposed, okay? We're not trying to influence it. We're just looking at the data and trying to make sense of it. An experiment is where treatments are imposed. A treatment being something imposed on a group of people to see if that affects something. And then we have to have multiple treatments, or at least a control group or a basis of comparison, so we can see that improvement or decrease in whatever we're measuring. It allows us to show cause and effect. Experimental units, who the treatment is imposed on, a lot of times it's people, but it can be animals or anything, objects. Treatments are what is done or not done to the experimental units. So that's just kind of a baseline for experiments. We'll get a little bit more into it in the next part of the lesson. So let's get on to the check your understanding. Pause the video, read through the check your understandings, and see if you can answer all the questions. Once you've unpaused it, then come back and we'll go over the solutions. All right, thanks for attempting. Let's see what you got. So do homes with metal roofs get worse cell service than homes with shingled roofs? Ben and Jerry are neighbors and own an ice cream business together. Ben has a metal roof on his home and Jerry has a shingled roof. Ben and Jerry select a random sample of 50 employees. They randomly assign them to come to a party at either Ben's house or Jerry's house. When they arrive, Ben and Jerry ask them about their signal strength. Was this an observational study or an experiment? Justify your answer. Hopefully you said experiment. People were randomly assigned to either house. Treatments were imposed, house with metal roof versus house with shingles. So this was an experiment. So good job if you chose that. Number two, study shows that one factor that strongly correlates with student academic success is the number of books that the family has in their home. Researchers randomly selected 100 students and measured their academic success, as well as counted the number of books their family has in their home. Is this an observational study or an experiment? Justify your answer. What'd you say? You're right, observational study. We're not imposing any treatments on people, no random assignment to different groups to compare. Students were simply selected and their academic success and number of books were measured. No comparison was made. So, there's other variables that play into this. For instance, the explanatory and response variables, the explanatory being how many books they have versus the response, academic success. And usually it's something you want to measure. So GPA, SAT, ACT, something to show academic success. But this was not an experiment. So there's not a whole lot of cause and effect here, right? Explain clearly why such a study cannot establish cause and effect, such a variable that may be confounded with the number of books that the family has in their home. Well, let's talk about that. People were not randomly assigned. So full stop, no random assignment, you can't show cause and effect. There has to be random assignment. So you don't have to say much more than that when you're trying to answer something like, why can't there be cause and effect? People were not randomly assigned to be in homes with many books versus not many books. No comparison was made. For example, and here's an example I come up with, families with more time, money, resources can help students achieve greater academic success anyway. These people likely will have more books at home. So it's not really known whether the books themselves will cause this to happen or the resources the family has is going to be what causes this, or natural inclination of the student in general. So there's a lot of factors here at play. These are confounding variables. Okay, our next lesson. This is a video that I really don't want to take up extra time here. So when you click on this document here, it'll talk about the effects of the placebo effect using a fake power drink. So play that video. You can go to this URL if you're just watching from La La Land, and come back and let's answer the question. Why do you think the people in this video got stronger? Well, think about what happened, right? They gave these people a fake drink. They were saying it's a power drink. These people have it in their head that they're going to be stronger, right? So they thought they were going to be stronger, so perhaps they tried harder. That's called the placebo effect, y'all. You probably heard of that term before. Similar to the video, the teacher wants to use a beverage to test the effect of that caffeine can have on heart rate. So here's the initial plan. We're going to measure initial pulse rate, give each student some caffeine, Coca-Cola, wait for a specified time, measure final pulse rate, and compare final and initial rates. What are some problems with the plan? What other variables will the sources of variability in pulse rates? So let's talk about some problems first. First thing I would say is there's nothing to compare to. Okay, we have measured everyone's pulse rate. We gave everyone caffeine, and then we measure their pulse rates after. There's sugar in soda that might have an impact it. People know they're getting caffeine, so they have that placebo effect already. So you got to have some sort of baseline. In this case here, it's probably best to say, well, all right, I'm gonna measure these guys before Coke. Then I'm gonna give them something I think is Coke, but maybe it's not. Maybe it doesn't have caffeine. Maybe it's caffeine-free Coke. I then compare their pulse rates. We can see if there's this natural inclination to say, hey, I think I got something. I'm going to be more energetic. So in this case here, there's nothing compared to. That's called a control group. There's other variables in play, confounding variables like sugar, and for instance, and people knowing they're getting it. We need to have some sort of blinding. They have to not physically cover their eyes, but they have to not know that they're getting a caffeinated beverage, or not know which one they're getting. I guess if they know there's a caffeine-free versus caffeinated, they should not be told that. Okay. And really, the experimenter probably shouldn't know either, because they don't want to like influence the person drinking the drink. You know what I mean? So, just think about that. That's single blind is just if the one group doesn't know, but double blind is if both the experimenter and the person conducting the experiment, experimentee and the experimenter both don't know. That's double blind. So let's go back to let's design this experiment effectively. Okay, design an experiment to test the effect that caffeine has on heart rate. What we're going to do is we're going to take the students and randomly split them into two groups. I give one regular Coke, the other caffeine-free, without either group knowing which Coke they're receiving. Compare their change in heart rate. So you want to explain that. And again, randomly split. So random assignment is key. And then we want to go down here and we want to, sorry, I thought I had my little layout there. Maybe it's the next one. Yeah, here it is. So we want to be able to kind of visualize what that looks like. So I don't know the number in the groups, but start with N students. Do some random assignment. Split them into two groups, okay? equal size groups randomly assigned. One of them is going to get regular Coke, one's going to get caffeine free, and then we're going to compare the change in heart rates. This will give you a baseline, a comparison. Okay, some more important ideas. For a control group, it's used to provide baseline data for comparison. A blinding is when subjects, not physically blinding, but they don't know what treatment they're going to be getting. So when subjects and experimenters who interact are unaware of what treatment is given. Single blind is only subjects or the experimenter, but not both, is unaware. Where double blind, both subjects and experimenter are unaware. Placebo effect, of course, is when a fake treatment works. Okay, caffeine-free Coke miraculously made them more energetic because I think they were getting caffeine. Okay, conducting a random assignment to treatment groups. We want to label everybody. We want to randomize it and assign them to whatever groups. So make sure random assignment always is done. Otherwise, you have no experiment, my friends. You got to have random assignment. That helps you compare things. And so there's 4 principles of experimental design. 1, comparison. 2 or more treatment groups. Can't have 1. All right, you got to have at least 2 groups. Sometimes you have 3, sometimes you have 4, but at least 2 groups when you're making comparison. Duh. You got to have random assignment. Control. You got to have something to control things. Keep all variables other than treatments constant. So our next lesson, we'll talk more about how to implement more effective control methods, but we want to make sure we can reduce the effect of confounding variables. And then replication. Got to have enough people to make this convincing. So we use enough experimental units to distinguish the differences. All right, a little more check your understanding, and then we'll be on our way. Read through this question, pause the video, try it on your own, and then we'll check it. You didn't pause the video, did you? Pause the video and try this on your own. That's better. A group of researchers in Africa find a creative way to protect cattle from lion attacks. They paint eyes on the cow's rears. That's kind of weird. To determine if this treatment is effective, they randomly assign the cattle to one of 3 treatments. Eyes on their rear, cross marks on their rear, or nothing on their rear. After 4 years of roaming the plains, the cows with eyes saw no deaths. This got really morbid. The cows with a cross suffered 4 deaths. And the cows with no marks suffered 15 deaths. Hey, beef, it's what's for dinner. But you can see that there was some sort of effect on the markings on their butts. Now, let's look at the question. Why was it important to have a control group that didn't get a mark on their rear? Well, you know why. You got to have some sort of basis of comparison. The control group helps gives a baseline to compare to. It's important to know the typical amount of lion attacks without any influence to see how much, if any, the markings or eyes would decrease this number. You got to know what they're starting with, right? So you got to have control. Suppose the researchers had 1,200 cows. Describe how to randomly assign the cows to the treatments. Well, there's several ways to do it. Here's one way. Number each cow 1 through 1,200. Use a random number generator to select 400 cows, ignoring repeats. These will get the eyes. Repeat this process for the next 400 cows. Again, ignoring repeats or those already selected. These will get the cross marks. And then who's ever left is in the control group. There's your random assignment. There are many ways to do that. There's one. C, what's the purpose of randomly assigning treatments in this context? Why do we randomly assign? We want to minimize the effect of other variables that might attract or deter lions, such as size, age, speed, sex, etc. These are confounding variables. We want to minimize the effects of it. We randomly assign. We want to have some sort of baseline of comparison. We also need to show cause and effect. We cannot show cause and effect without random assignment. In fact, I don't know why I didn't type that on there. There. That is super important for cause and effect, random assignment. So if we use a convenient sample, for instance, we might assign one treatment to similar claws that are together, so we wouldn't know which of the other factors contributed to the lion attacks, right? We can't show cause and effect unless those confounding variables are reduced. Next question, create an outline showing a completely randomized design for this experiment. Here's what I got. Read through it, see if it makes sense. Like a little flow chart. It's kind of fun. Anyway, hope this was helpful, useful. You should be able to follow up by reading section 4.2 and watching the videos that are assigned in AP Classroom, and we'll get back on it. Again, there'll be a sapling assignment going over this whole section after we go over the next part of it. It's a big section. So y'all have a great rest of your day, night, evening, afternoon, whatever time it is of day. Appreciate you. Bye.